Florida State University, who will lecture us on a new model for partial hyperbolic dynamics in dimension 3.
Thank you.
Obrigado,
So
Sérgio.
first of all, I want to thank for the invitation to speak in this conference, and obviously I'm very happy to be here on Paul's conference for 85th birthday. Happy birthday, Paul. I'll forget at the end, and Paul has been a big influence in my mathematical career. I've met him, I think, just before I graduated, and I've been coming to lots of conferences here in Brazil, and there he is taking very careful notes, making very sharp questions, and you know, it sort of inspires me, you know, oh, I can keep going for like 20, 30 years more. All right, so I'm going to talk about partially hyperbolic diffeomorphisms. So mostly it's going to be in dimension 3, but I mean, they occur in lots of dimensions. So first we're going to define them. So first, this is joint work with Thomas Barthelmy and Raphael Patry. Okay. So sort of the goal is to sort of understand partially hyperbolic. I will denote lots of times by pH. So understand pH in dimension 3. Higher dimensions, I think there's more possibilities. All right, so first, a definition. F diffeo of Mn is partially hyperbolic if the tangent bundle is split into a Whitney sum. So S for stable, U for unstable, and C for center. So this is the bundles are invariant by the derivative. And then there's, you know, stable bundle, you're going to contract. Unstable bundle is going to expand. So for any x in M, for any V, let's say Vs in Es of x, Vc in AC of x, and Vu in EU of x of unit norm. So first, the size of Vs is less than 1. The size of VFE of VU is bigger than 1. So contracts the stable vectors, expands the unstable vectors, and what happens to these ones? So df/Vs is less than df/Vc and is less than df/Vu. So the center is just sort of in between. You may contract, you may expand, you may stay the same, but if it contracts, cannot contract more than any stable vector in that point of unit length, and cannot, if it expands, cannot expand more than the unstable length. So this is a point-wise definition. There's also what's called the absolute, where you would be sort of without, depending on the points. Okay?
The spaces have dimension 1?
No. No.
What do we know about the dimensions?
Right. So this is continuous. So dimension of ES is fixed, and same thing for EU and EC. And obviously, you want them to have dimension bigger than 0. So if it was EC was dimension 0, then you would have a Nosov diffeomorphism. Okay? So why the interest? So essentially, they are the only ones which can be robustly transitive and stably ergodic. So that's why there's interest in understanding them. So now, addressing your question again, I'm going to, from now on, M is going to have dimension 3, and then all of these are going to have dimension 1. So for the rest of the talk, we're going to think of them, all of them. Right. So, right. I mean, obviously, the higher dimensions have a lot of interesting things, but you know, we're going to do this. Okay. So, so some basic examples, and there are 3 examples that are very common in dimension 3. They are very easy to come up with. So first, linear autapomorphism of the torus with 3 distinct eigenvalues. And let's suppose that they're positive, just for simplicity. Okay. So, but the thing here for this one, I want this thing. Okay. So obviously, this is bigger than 1. This is smaller than 1. And the eigendirection of the smaller eigenvalue generates the ES, this generates the EU, and this generates the EC. Okay? So you split the tangent bundle of the torus, and it's the same everywhere in invariant by translations. And here you can see that you could have this equal to 1, you can have smaller than 1 or bigger than 1. So the center could be expanding, contracting, or invariant. Okay? A second example is in, it's called like skewed. And I think I'm going to do sort of, you can do more complicated things, but you can do it in T2 cross S1, also in new manifold. So we're going to have some F of P and T is going to be, let me get the formula here so that I don't mess up. So this is going to be BP. So B is an hyperbolic matrix. And let's suppose with positive eigenvalues, so lambda 1 and lambda 2. And then age of T, so that let's do these eigenvalues here. Lambda 1 less than lambda 2. So 1 is bigger than 1, 1 which is smaller than 1. And the age, so that the derivative here of age is less than lambda 2 and bigger than lambda 1. So here, this is the center. So this is going to be the center direction. And this will generate the stable, this will generate the unstable. Okay? So here it's a little more interesting that you can have some points the center can be contracting, other points it can be expanding, as opposed to here where, you know, the way I did it, you know, the center it has to be, say, contracting everywhere or expanding everywhere. Okay? And the third example, so we're going to start with a Nosov flow. So what is a Nosov flow? So phi is going to be a smooth flow, and it's sort of similar to this. It's sort of essentially the continuous version of that, and the third example would be a discretization of this. So the tangent bundle of this is ES. Let me change a little bit. So the stable of the flow plus the tangent direction of the flow plus the unstable of the flow, also invariant by the flow. So this is stable. This is unstable, and the other one is the flow direction. And let F to be the time 1 of this flow. Okay? So for here, this is partially hyperbolic. The stable direction of this is the same as the stable direction of the flow. Same thing for the unstable. And the center direction is the tangent of the flow direction. Okay? And you can also do this more complicated sort of a variable time, t of x, where t of x is bigger than 0 and smooth. So this is time 1, this is variable time. Okay? So these are the 3 basic examples. Right, so then there was a question and conjecture, which was essentially this all the 3 examples that you have in dimension 3. So maybe some people in the audience actually know more about this than me, but if I understand correctly, Fuhrhaus asked this question in 2001, and then Bonatti and Wilkinson wrote this in a paper as a question. Then it was understood as a conjecture. So essentially, it's saying that under certain conditions in dimension 3, you're going to have this. So if F, pH, and dimension 3 is transitive, then F is what is called dynamically coherent, which I'm going to define later, and leaf conjugate to 1 of 1, 2, or 3. I'm also not going to define leaf conjugate. But essentially, this is sort of saying equivalent. Okay? And this conjecture was open for about 15 years, and it actually generated a lot of research in this field. And so not true. Now there are many counterexamples. And my goal here is to describe some of these counterexamples. I mean, they fit into another model. I'm going to describe this model. I mean, it turns out that there are several ways to several flavors of this new model, and some of these flavors are equivalent to the other ones, and so on. So this is what I want to talk about. Right, so if you go here, so first of all, this first 2 are very restrictive. So this is T3, this is nilpotent. And so this is essentially, if that conjecture were true, essentially it would be this. And this, you notice in particular that F is homotopic to identity. So it doesn't do anything to the topology. Okay? So I'm going to describe, there are several counterexamples. I'm going to describe one family because, you know, it's sort of, you can see a certain behavior, which is the behavior that sort of motivated us to define this sort of new model. Okay? So let me go here. The examples that I'm going to describe are actually not the first ones. They were ones that were before, but so here a counter examples. So this is in this is by BGHP, B for Bonatti, G for Gogolev, H for Hammerlin, and P for Potry. So this is in M, which is T1S, S hyperbolic. So in particular, hyperbolic surface, we know that we have the geodesic flow, which is a Nosov, so we have this type of partially hyperbolics there. Okay? So what they proved is that for any G, a mapping class of the surface, there is F in M, which is partially hyperbolic, and induces G in the mapping class groups of S. So, and I'm going to talk about one very particular case, which is the case of Dan twist. So let's see, G, then twist on a curve alpha. Here's my S, here's my curve alpha. So then twist, you know, you're going to have the identity outside of a neighborhood here, and in this neighborhood here, you're going to do what's called a then twist. So the image of a arc that goes straight across is now going to go like this, and so you do one twist, okay? And this is a diffeomorphism of the surface, which induces a diffeomorphism in the unitangent bundle, okay? So they did a lot of things in this paper. So one of the things that they did was suppose that alpha is extremely short. So I'm going to redraw this surface. Here's my alpha. Okay. So you can do the then twist. So because this alpha is very short, so the then twist, you're kind of twisting around it, but the length of alpha is very small. So you can do the twist perturbing geometry in M very little. Okay? So what they do is, essentially this is the effect on the topology. But this is not going to be partially hyperbolic because, you know, it doesn't have the stable and unstable bundle. So you're just essentially doing things in these vectors here. So what they're going to do, okay, I have the geodesic flow, and if I flow a lot, then I have this partially hyperbolic behavior. So I flow a time, say a time 100 billion, okay? So I have the partially hyperbolic behavior. Then I do the then twist, and then I flow again. So their examples are, F is going to be phi T1 composed with the, let's call this then twist here, no, let's call it this, H. H composed with phi T2. Okay? So for T1 much bigger than 0 and T2 much bigger than 0, F is partially hyperbolic and induces then twist in the surface. Okay? So the idea is that I'm not going to get into the details because it's not really the goal of this talk, but the idea is use transversality. So geodesic flow. So you have the stable and the flow direction, and you have the unstable and the flow direction. Okay? So when you flow a lot, it sort of pushes things very close to the unstable direction because the unstable are expanding much more. And then you do a little bit of change in geometry, And then you flow a lot, so sort of unstables are going to be close to the unstables, and stables and flow direction, and the same thing. So with the transversality, sort of implies the partial hyperbolic behavior. So transversality, I'm sorry? The flow, sorry, the geodesic flow.
But you're starting with a partial hyperbolic.
No, I started, so I'm trying to construct examples here in this manifold here, okay? So you start with there has a geodesic flow here on the surface. Yes, geodesic flow. So then you flow a lot, so that's okay, that's partial. Then I do a change in geometry, and then I flow a lot. So here, a lot of change in the geometry. Here, small change in geometry. Here, a lot of change in geometry. But here, no topology. Here, some topology. And here, no topology. So the topology is contained in here, and the geometry is here. So it's very interesting. And they can do this, then combine this, and so on. Okay. So that's how they achieve this. But I want to, so this is the properties that I want to concentrate. So you flow a lot, then the small change in geometry, and you flow a lot. So what they obtain, so properties, so the ECS of F very close to the ESI of the geodesic flow. And the same thing for ECU, very close to the ones of the geodesic flow. Okay? So in particular, the EC of my F very close to the flow direction. So this is one thing that they get. It's almost for free, but also for any flow line of the flow, there is a unique curve tangent to EC of F, which tracks it very close, and vice versa. So there's sort of a correspondence between the flow lines of geodesic flows and curves which are tangent to the center bundle of the partially hyperbolic diffeomorphism. These curves which are tangent to EC, so curves tangent to EC, I'm going to denote them by center curves. So what this is saying is flow line associated with center curve, and center curve associated with a flow line. This is a bijection. So this is what I'm going to try to sort of mimic in general. There's an nozzle flow. There's my partial hyperbolic. Sort of curves which are tangent to the center, so going to be associated with the flow lines of the flow, and vice versa. However, a nozzle flow, I mean, you're flowing, and you think, okay, I'm just going to take the time 100 map or a variable time map. It's not, because, you know, in this case here, there's something, the deformers is doing something to the topology, and flowing anytime is homotopic to the identity. So, you know, there's an nozzle flow there, and it sort of encodes something, but it's not just a variable time of a nozzle flow. Okay? So this is the goal, and there's the first definition, which is what's called collapse on nozzle flows. It's just this. It's one-dimensional. The other definitions involve sort of two-dimensional foliations associated with the partially hyperbolic diffeomorphism, sort of very similar to what you have for a nozzle flow. So this and this are integrable and produce the weak stable foliation of the nozzle flow, which is two-dimensional, and saying this and this produce the two-dimensional unstable foliation of the nozzle flow. We're going to have these foliations for partially hyperbolic, except that they are a little bit different. They are called branching foliations, where you can have merging. So I'm going to have a couple of preliminary definitions, and then we're going to start with the first definition. We'll see how many definitions I'll be able to do. But sort of the goal is this. There should be sort of a relationship between flow lines and sort of center curves which has some properties. Okay? So before I define anything, I'm going to first I'm going to have a generalization of the notion of an nozzle flow, which is more appropriate here. It's called topological nozzle flow. And this kind of relates just the objects, the flow lines, and the center curves. But there's something further, which is the action of F here. How does that relate to something here? Well, it turns out that what it relates to here is an orbit equivalence of the flow that sends flow lines to flow lines. So I'm going to define these two things, and then I'm ready for the first definition of this sort of new model. So first is what's called a topological nozzle flow. So what I'm going to have is less regularity than an nozzle flow. So in a nozzle flow, so for instance, this is integrable, and this is integrable, producing one-dimensional foliations. I'm going to lose this stable bond in this. I'm going to have the two-dimensional foliations, okay? So phi in M3 closed is TAF. If no point orbits, flow lines are C1. There are two-dimensional foliations, FWS, FWU, for weak stable and weak unstable, invariant phi, topologically transverse, and in a leaf of the stable, all orbits are forward asymptotic, and in the other one, they are backwards asymptotic. Okay? But I don't have the strong bundles and these foliations. I don't know exactly what is the regularity of these two foliations. Okay? This appear a lot in the setting of three manifolds and topological, what's called pseudo-nozzle flows as well. Okay? All right, so the second definition, an orbit equivalence of a flow. Well, let's do it without point orbits, which is sort of the case that I'm interested in, is a homeomorphism orbit equivalence between flows is a homeomorphism that sends orbits to orbits and preserves orientation on the orbits or flow direction. And the self-orbit equivalence which I'll denote by SOE, is an orbit equivalence flow to itself. So the self-orbit equivalence is going to be sort of the action on the flow side the partially hyperbolic F is going to be the action on the partially hyperbolic side. Okay? So I'm ready to define my first definition for this sort of new model. So this is going to be collapsed Another flow, which will be denoted by CAF. So F, PA, in dimension 3 is CAF if there is a flow, which is a topological another flow, and a SOE beta of the flow, and there's a map, like essentially this map is going to associate sort of flow lines to center curves. But this map is actually going to be a map between the manifolds. So this is sort of a correspondence between the collection of flow lines to the collection of center curves. Now I'm going to have a map from the manifold to itself that's going to send the flow lines to center curves. Okay? So then there's a map, H named to M, homotopic to the identity, so this H is the map that should send flow lines to the center curves. So H is differentiable along flow lines and sends orbit of the flow to a curve tangent to EC, so a center curve, and derivative never zero, so never backtracks. Okay? That's the first condition. And then the second condition is kind of saying that the beta is telling me what the F is doing via this H. So the H provides a semi-conjugacy between the beta and the F.
What is beta? I didn't understand.
So beta is a self-orbit equivalence of the flow. So it's kind of shuffling of the flow. Okay? And here's where it's going to come in. So for any x in M, let's see, H of beta of x is going to be F of H of x. Okay? So you have, so here you have a collection of flow lines. This is on the flow side. And then you have beta, kind of a sort of a shifting of the flow lines. And here you have curves. I guess I have to do a closed curve here. And this should be tangent to EC. And my H is sending things which are flow lines to things tangent to EC. And they commute. So then the F here, beta and then H is the same as going H and then F. Okay? So like I said, the H is a semi-conjugation between the beta and the F. Okay? Any questions up to this point? So, right. So I guess I sort of I didn't write, but I already talked about this map collapsing. Okay? So first of all, notice H need not be homeo. Okay? And in general, it will not be a homeomorphism. Because if it was, then in particular the stable, we can stay stable, and we can stable with projective foliations, and sort of would be a sort of a restrictive condition. So let me give you an example. So example, suppose that F is time one map of another flow. Okay. So then I'm going to take, so this is a collapse. Oh, and I already know that is another flow. Time one map is partially hyperbolic. And I'm going to claim that it's CAF, and that's very simple. So you're going to take H to be identity. So H is going to do nothing. And my beta is going to be my F, which is the time one map. So obviously beta, so it's time one map. So this is a self-orbit equivalence, which preserves every orbit. So there's no shuffling of orbits. So you just flow along the flow line for time one. Okay? This is what's called a trivial self-orbit equivalence because it preserves every flow line. But in general, it's not going to be like that. So BG, HP examples are CAF, even though it's not so easy to see. So in that case, obviously, we have the candidate for the nozzle flow, which is the geodesic flow. And we have, we don't have quite this map here. We sort of know how to relate orbits with the curves which are tangent to the center bundle. So you have to do more work, and I may say more about this later. It turns out they are a stronger type of CF, which I'll get to define soon. Okay? Right? So this was the first flavor, which is just one-dimensional, just flow lines and center curves. So now I'm going to relate, yes? Good question. Thank you, Thierry. Okay. So, right. So we know for sure it's not a homeomorphism if the induced mapping class is pseudo-Nosov. That's a theorem. You have to do it. And if the mapping class has a pseudo-Nosov component with at least one prong with a three-prong, lots of cases. It's not known in the case that was actually doing more, the case of Dan Twist. That's not known. And we tried a lot. We can't answer yet. Depending on the month, we think it could be a homeomorphism. Depending on the month, we think it's impossible. Okay, so now I'm going to talk about sort of the two-dimensional situation. And what I want is to sort of, first, the tool that we use is what's called the branching foliation, which is sort of the generalization of the weak stable and weak unstable. So let me talk about that. So there's going to be 3 more flavors of CAF. They all involve two-dimensional foliations, which are called branching foliations associated to the F, which is partially hyperbolic. Okay? So recall, so F partially hyperbolic, we have ES, EC, EU. So these two stable and unstable are hyperbolic bundles. And they are therefore uniquely integrable to foliations by work of Anazov. And what happens to EC? So, I mean, actually, for this one, hyperbolic bundles being integrable, there's no restriction on dimension, any dimension. Okay? So the EC we don't know, and there are examples which are not integrable to a foliation, or, I mean, there's lots of things that can happen. Also not, maybe integrable, but not uniquely integrable to foliation, and so on. So we're not going to really use this too much, but I already used these dynamically coherent. And this means that you can integrate the sum of this bundle and this to a foliation. So if ECS, ECU integrate to F invariant foliations. And in particular, the intersection of those two foliations is going to be a one-dimensional foliation, which is invariant by F and which is tangent to EC. That would be called the center foliation. Okay? So in general, we don't have that, but there's an amazing result set that we can get something which is this branching foliation. So I'm just going to define that. So more generally, and this is now strictly in dimension 3. So this is in dimension 3. There's a theorem by Burago and Ivanov. It's a little bit tricky because it has some conditions. The conditions have to do with orientability of the bundles. So if the bundles are all all orientable, plus df preserves orientations of these bundles, then there are f invariant, what's called branching foliations, WCS, WCU, which are tangent to ECS and ECU. So branching means leaves can intersect but not cross. And this is better seen in the universal cover. So in the universal cover, I'm going to have one leaf of WCS, and I may have another leaf which intersects it. So two different leaves. This is okay. What is not okay is if they cross. So this is no. This doesn't happen. Okay? So you don't have a sort of a splitting of the manifold in different leaves. The point doesn't determine the leaf. Okay? But this doesn't happen. Okay? If you're interested, I can talk to you more after the talk. It's a beautiful result, very technical, but right. So, and this kind of, these foliations sort of behave, like weak stable and a weakened stable of anosoplos. And also they essentially behave like rayless foliations. So in particular in the universal cover, they are properly embedded planes, which is something that Burago and Ivanov proved as well, and so on. Okay? Right, so one more fact. One can define branching foliations even without the orientation conditions, which is sort of all the properties that they satisfy. F invariant branch foliations, which are tangent to this. the orientation conditions guarantee that you're going to have these branch foliations, but it could be that you still have the branch foliations without the orientation condition. Okay. Now, under the orientation conditions, and basically here I mean say WCS transversely orientable. Now it's a branching foliation, then Burago-Ivanov again, approximated by actual foliations. Approximated actually very close, so the tangent bundles of this leaves here and this are also very close. Okay? I can talk to you more about that if you want later. You are not a beautiful rule, but they're very technical. Right, so this is the tool that we want. So this can always be achieved. So orientation, condition. These conditions can be achieved in finite cover. So we can always lift to a finite cover so that the bundle is orientable. And lift of finite iterate of F. Okay? And I should have said that in the Puhal's conjecture, the conjecture was also up to a finite lift and finite iterate. If you don't have that, then you can get easy counterexamples. So a lot of work on a partial hyperbolic in dimension 3. You know, you want to use these branching foliations. You take, you know, a finite cover and a finite iterate, and you prove something there. And then you want to prove something for the original object, which a lot of times turns out to be very complicated and involves sort of lots of things, including uniqueness of these branching foliations. So for the rest of the talk, which I don't have so much time, but usually I'm going to assume the orientation conditions, you know, if I need, without saying too much. Okay? Right. So I'm ready for the sort of the next definition. So I had the CAF definition. I'm going to have the next definition, which is the same thing except that in dimension 1 is going to be dimension 2. Okay? Right. So. I guess this is going to be definition 2. Strong collapsed nozzle flow, which is going to be as CAF. So FPH in dimension 3 is SCAF if there is a topological nozzle flow phi. Right. A self-orbit equivalence beta of the flow, a map H from M to M homotopic to the identity. So that is just going to have one more condition which has to do with the sort of the 2 dimensions here. So first is H is C1 along orbits, non-zero derivative, and maps flow lines to curves tangent to EC. So this is the same as I had before. And the second condition is sort of where the 2-dimensional stuff is going to come in. So age of the weak stable foliation of the flow is a branching foliation for F and tangent to ECS And same thing for the other one, tangent to ECU. And then finally, the third condition, which is for any x in M. Age composed with beta of x is f composed with age of x. So the first and the third conditions are exactly the same as before. It's just that I have now the age mapping the weak stable and weak unstable to branching foliations per f. Okay? So this is a stronger thing. And the difference here is that if this is true, then I have the two-dimensional branching foliations to work with. So it's the difference for people in three manifolds and foliation theory. It says it's the difference of having sort of a flow in the three manifold and essentially a rayless foliation in the three manifold, actually two rayless foliations. Okay? All right. So let's see. What do I want to say here? Great. Okay. So again, any example of EGHP is SCAF. As it turns out, I think all the examples that we could determine what they are strong collapse on nozzle flows. Okay? Right. So we're going to restrict to WCS and WCU having Gromov hyperbolic leaves, and this condition is very general. So if pi 1 of m is not virtually solvable, then any branching foliation for a pH in M has Gromov leaves. So T3 actually is very special in for partial hyperbolics in dimension 3, and sort of small manifolds are very special. Okay? How much longer do I have? 5 minutes. I started late. 5 minutes, ok. Eu acabo já. Peraí. Deixa eu só enunciar as outras duas. Oi? Não, 5. Eu preciso fazer as duas definições e enunciar algo. Ok, peraí. Então, mais duas definições e só... ok. So definition 3. So this is called leaf space collapsed nozzle flow is LSCAF. So F pH in dimension 3 is leaf space CAF if F has branching foliations, WCS, WCU, and there is a topological nozzle flow phi in M, and a pi 1 M equivariant homeo age from O to LC. This is the orbit space of the lifted flow. And this is the center leaf space of F tilde. So, okay, if you have branching foliations, then when you intersect, you have a one-dimensional center foliation. So this is sort of the center leaf space in universal cover, and this is the orbit space of the flow. Okay? Again, if you want to ask more, there's no sort of map here, but there is a map here that's hidden and is very easy to to figure out that. And the last definition is a geometric definition. Which has to do with the geometry of leaves. Okay? So, quasi-geodesic pH, which is, we say QGPH. So FPH in M3 with branching foliations, WCS, WCU, with Gromov hyperbolic leaves, is QGPH if center curves in universal cover, so intersection of these two foliations in universal cover gives you center curves in universal cover, are quasi-geodesics, not in the universal cover, but in their leaves. In the leaves of the lifted center stable and center stable. So think geodesic flow. So in geodesic flow, the universal curve of the stable leaf is H2, and the flow lines are geodesic. So this is it's a purely geometric property. And let me finish by just stating one result. I mean, this result actually, some implications are stronger that I'm going to state. I'm going to state it, sorry, because of time, I'm going to state it assuming all orientations, everything is orientable. So here's the theorem. Assume F as branching foliations with Gromov hyperbolic leaves and transversely orientable. Then SCAF, if and only if LSCAF, if and only if quasi-geodesic pH. This implication doesn't need orientation. This implication needs orientation just of one of the foliations. This implication doesn't need orientation. This implication needs orientation for both foliations. Okay? All right, let me stop here. Thank you so much, and happy birthday, Paul.
Thank you, Sérgio. I don't think we have time for questions, so questions could be asked later on at this cocktail. So now we are going to have a session of testimonials. So I would like to ask speakers to come with me stage.